Hello everyone, welcome to Amateur Hour, the show in which we teach ourselves how to program in courses of about 1 hour. We're following the CS50 course and we're on to the third lesson so far. We're going to be learning about sorting algorithms, and I've got sorting algorithms running here in the background, found them through YouTube. So I guess we're going to hear a few things about how this works. We have to go on to the show, on to lesson number 3. So we talked a bit about how last week was all about memory and about arrays, and he talked a bit about how a string is an array of characters. An algorithm should be efficient. That is to say, use very little time to come to the right answer. Oh, and he also said that it would be nice if it doesn't use too much memory to come to the correct answer. A big O notation is used for the running time for your algorithm. Okay. He just explained that even if you were to have a formula where you divide the total amount of steps needed to come to the correct answer and then divide the total amount of steps by 2, then as long as your number of total steps becomes extremely large, you wouldn't really care about it being divided by only 2 once. Say your number gets close to, well, 1 billion, it would still take 500 million steps before you get to the right answer, and in that case is somewhat close to the original amount of steps needed, and that's why they say it comes into O divided by N. We have big O, runtime, the upper bound of how many steps an algorithm might take. Okay, so if you go into an algorithm and you try to find the number 10, and it writes down every number starting from 1 up till 10, the runtime, or the most amount of steps the algorithm will take is 10. The lower bound of your runtime, if you're looking for a number and your set is the numbers 1 till 10, and say you're looking for the number 1, the lower bound of your runtime of your algorithm will be 1. And then we have a lower bound and upper bound that are the same, which is the big theta, he called it. So we have big O, omega and theta, and that was when the lower bound and the upper bound of your algorithm are the same. Aha, I get now why you first wanted to talk about having n steps divided by a constant number doesn't really matter for your runtime that much, because we had the I from 0 to n minus 1, and then we have an if and the return true. He says that the if it is the number and the return true are just as if you were dividing by a constant number, because they are constant steps. So those, in the big scheme of things, will not matter. So I guess we were right about it being a big O brackets n, but we didn't at the time fully realize why. Yeah, that was exactly correct. Okay, good.
Good job!
Alright, we used a better sorting algorithm. We first made sure that all the numbers were in the correct order, and then we decided to go, okay, let's go to the middle and then check that number and see if we have to go to a higher or a lower number. And then we go to the middle of the remainder again and check if we get to go higher or lower again and go to the middle again. Well, this way we found the correct answer in only 3 steps, so that's nice. Okay, and it's called binary search. Okay, so now he showed us pseudocode of the binary search, and there's something I'm not too sure about. We have a number behind the door, middle. Say we're looking for the number 5, and we say door middle, we open it up, and we show the number 3. So we don't return true in this case because 3 is not equal to 5. And then we say, well, the number we were looking for, 5, it's bigger than door middle's number. So no, we're not using this if number is smaller than doors middle. This is not true. So we're not going to search doors 0 through doors middle minus 1. We're instead going to search, because number is bigger than doors middle was of course 3, number was of course 5. We're doing this part of the code. We're searching doors middle plus 1 through doors n minus 1, because n minus 1 is the end of the array. What I don't get is why you would only divide once. You only once say what the middle is of your current doors. So then we're checking every number of the doors now, instead of dividing each time like we said just a few minutes ago, which I think would lead to a much more efficient search. Of course, the last thing we didn't talk about is if there are no doors left to look behind, then return false. Okay, so he did say that the amount of steps left would be log n. So I guess that I misunderstood the pseudocode.
Just a little patience.
Yes, every time you've done a step, you would check the new middle of the doors remaining and take that for your algorithm. He just explained that the omega, so the best case, the lower bound on running time for a log n and an n search are the same, because you could be lucky and find the number you were looking for on the very first try. But he also said that the lower bound is not that often that useful. You're more interested in the upper bound, so the big O. He's posing the question that sometimes you should just start linear searching, and sometimes you will want to sort your data before actually searching for the answer to your, in this case we were using numbers, but it could be anything in your data set you're looking for. So sometimes you will be sorting first, and sometimes you will just start looking. One of the situations in which you would sort first is if you're searching the same set very often. So we were not allowed to compare an array stored under the place I to another string. So comparing a string stored under I to a string was not allowed here. Okay, and we will be using string compare strcmp to compare two strings. Okay, I'm going to guess that we're going to use this in our assignment, so I'm going to point it out. String compare strcmp brackets open names square brackets I, and then you can compare it to a string. So okay, gonna use this probably. Gonna probably have to rewatch this probably. What if someone is ever in the phone book but they don't have a number? The number is not known? Then this program will very soon start giving wrong phone numbers to whoever's trying to look up a number in this program.
All we need is just a little patience.
Oh, that's also what he's talking about now, that this piece of code is very accident prone. Alright, it looks like we've been working for just over 1 hour, and the professor is going to change from algorithms, well, start to explaining algorithms to data structures now. So we're going to leave that for the next amateur hour. I hope to see you in the next amateur hour where we'll be looking at data structures. See you then!